Okay, so here's a problem from the book. It's problem 431, and it wants the shear force and bending moment diagram for this structure. So again, you got a pin here at the left at an incline, a roller at C, there's an internal hinge at B, and then you've got this link over here. You'll notice that there's no length given for that link, so we'll have to be careful what that really means. Obviously, there could be a force there, right? But there's going to be what? No moment. There's going to be no moment at this hinge. There's going to be no moment at this support. Will there be moment above this roller? Yes, probably. So the first thing we want to do is try to find all the reaction forces and then draw the shear force and bending moment diagram. Now, can I do that? Well, how many unknowns at A? 2. How many at C? 1. How many at D? 1. It's a weightless link. It's 2 force members. So I've got 1, 2, 3, 4. I got 4 unknowns and 1 free body. That's not going to work. So I'm going to have to take it apart here. So I'm going to have to do a little statics just to get started. So let's look at first the free body diagram of section AB and see what we have. So I'm going to draw that. So at A, it's a pin, so I'm going to assume that I have a force in the Y direction and a force in the X direction. B is also a pin, so when I take it apart, I'm going to assume that I have a force in the B direction and a force, in the Y direction and a force in the X direction. And then I'm going to get a concentrated equivalent force for this section of the load. It's 5 kilonewtons per meter over 2 meters. So that's going to be an equivalent force of 10 kilonewtons. It's going to be applied right in the middle. So that's a distance of 1 meter and 1 meter. So I got 4 unknowns here. Some of them I can find, some of them I can't. What could I do? I could sum moments at A and get BY. Some forces in the Y direction get AY. I couldn't get anything in the X direction, right? I could just get that these are equal and opposite. Do I care about the X direction right now? No, I'm drawing shear force and bending moments, so it's really not a huge concern. So let's just plow ahead and see what we get. So using right-hand rule as my sign convention, let's sum moments at A. So when I do that, this concentrated equivalent force creates what kind of moment about A? Positive or negative? Negative. So I got negative 10 kilonewtons times a moment arm of 1 meter. And then BY creates positive moment times 2 meters. So it looks like BY is 5 kilonewtons, right? And then if I sum forces in the Y direction, what do we get? Well, I got AY is acting up, BY is acting up, and then my 10 kilonewton force is acting down. So it looks like AY is also 5 kilonewtons. And that shouldn't be a surprising result. It's kind of the load's applied right in the middle. You'd expect half to go to each side, and it does. So what if I pass this on to my free body diagram from B to D? So I'm going to draw a section that goes from B to D. Let's see what I've got. First, because I made these assumptions for BX and BY, they're going to be equal and opposite on this body. And now I'm going to make an assumption that CY, the reaction at the pin, is up, and also the reaction in this leg over here, I'll call it dy. I'll also have to handle the distributed load from B to D, which again, the area under the curve, it's 2 meters times 5 kilonewtons per meter, so that's 10 kilonewtons. And it happens right in the middle again, so that's 1 meter and 1 meter. Now remember, we know By. Okay? Oh, by the way, since we're here, what if I sum forces in the x direction here? What is Bx? 0. And then, of course, if Bx is 0, Ax is 0. So we're not really leaving those pieces out. We just really don't need them. But I do know By, so I want to find these two things. So I think what I'll do first is I'll sum moments about either C or D. And just because C comes first in the alphabet, I'll sum moments about C. So when I sum moments about C, I have By. That's creating positive moment. So that would be By times 1 meter. The distributed load, the concentrated equivalent of that, passes right through C, creates no moment. And then I have dy, which I assumed acts up, which creates positive moment. And it also has a 1 meter. So according to this equation here, dy is just equal to minus By. And what is By? 5. So it looks like dy is what? Negative 5. Which means it's actually acting down. Okay? So now I can sum forces in the y direction, and I should be able to solve for cy. So I've got By acting down, got cy acting up, and I've got dy acting up. Those are all my values, and then 10 is down. So I should be able to solve for cy. All right. Why did I put a negative there? Oh, it is acting down. So that's 5. So that's minus 5. Dy is another minus 5, which is minus 10. Minus 10 is minus 20. So it looks like cy is going to be 20. Okay? So now, believe it or not, almost 10 minutes into the problem, I can now draw the shear force and bending moment diagram. So let's extend my template. There's my beginning and end. Now I know something's going to happen here at B, so I'll add that. And I know because of my reaction at C, something's going to happen there. So I'll add that. So let's start off with drawing the shear diagram. All my values would be in kilonewtons. So my reaction at A, AY, I assumed up. Is that positive or negative shear force? That's positive. And AY is 5. So I'm going to start off at 5. Go all the way over here to D. What's D equal to? dy, oh, here it is. Dy is up. Now, what kind of shear force is that? That's negative. And what did dy end up being? Negative 5, so that means it's actually positive. So I should get a positive shear. What do you think of that? Well, let's see what happens. I've kind of run out of room here, so I'll have to do it down here. So remember, our change in shear is the area under the load diagram, and that the slope of the shear diagram is equal to the load. So starting here, what's the change in shear from 5 to B? It should be the area under this part of the curve, right? And what is that area? It's minus 10, right? So I'm going to start at 5, I'm going to subtract 10, and that brings me to minus 5. And what's the slope? Well, it's equal to the load, and you can see the load is constant and negative, so I should get a curve that looks something like that. Now, what happens when I get to the end here where BY is? Huh?
For sure there's no shade. Like you just...
Yes.
Why is it negative something on BY? BY is positive.
Okay, now say that again.
Why is the
Which free body are you talking about?
at the sheet? You're talking about
Right here?
Yeah.
Why is this 5?
Yeah, I get why that was 5, but why is it negative 5 on the second one? I think.
Oh, because the change in shear is equal to the area of the load diagram. And if you look at this part of the load diagram, right? What's the area of that curve? It'll be 5 times 2 is 10, and the load is down, so it's negative. Negative 10. So if I start at 5 and I subtract 10, I get negative 5. Now the interesting thing about looking at these forces as BY is that one's up some force and one's down some force. So there's really no applied force there, so there's nothing to do there. We just leave it alone. So what's the change in shear between B and C?
Negative 10.
Yeah, it's this area under the curve, right? Well, it's 5 times 1 is minus 5. So we're going to go from minus 5, we're going to subtract 5, and end up at negative 10, right? And what's the shape? Well, the slope is given by the load, and the load is still negative 5. So it's the same slope as before. Now, what happens at C? There is an external force, CY, right? And we found CY was up 20, so that means as I go from the left side of C to the right side of C, my shear changes by positive 20. So that means I should jump up to 10. And then what's the change in shear from C to D? Well, it's this area under the curve, which is 5, and it's minus, so 10 minus 5 brings us to 5, and we're all good. And again, the slope is the value of the load, and the load has the same slope. In fact, the slope of all these lines is the same. It's minus 5 to 1. So you get, this is your shear diagram. Okay? Now let's do the moment diagram. I'm going to run out of room. I didn't give myself enough space, so I'll try to squeeze it in here. So there's our positive moment, and we'll be looking at kilonewton meters. Okay, what's the moment at A?
0.
Should be 0. What's the moment at B?
0.
Should be 0. What's the moment at D? Should be 0. So this is the new one for us, is that we've got this moment at this internal hinge. We know hinges can't handle moment. Also, you'll notice that we cross the axis here, so we're going to pick up another kind of point of interest on our moment diagram. So what should be that value for x1? Now this one you don't even have to calculate if you look at it. These triangles are similar. This one has a height of 5, this one has a height of 5. So that means these two links should be the same. And if they have to add up to 2, it should be 1 meter. Everybody see that? If you don't see it, you go back to the same thing. The change in shear from 5 to 0 is 5. The area of the load curve would be x times 5. Solve for x, you get 1. So that's going to end up being 1 meter. So now let's do our moment. So we know that the change in moment is equal to the area under the shear diagram, and that the slope of the moment diagram is equal to the shear. So change in moment, change in shear diagram. What's the area of this part of the shear diagram? It's a triangle, so it's 1/2 base times height. I think that's 2.5, right? So I should get up to a value of 2.5. And what's my slopes? Should be equal to the shear. So the shear here starts off at a big slope and ends at a 0 slope. So I should have a parabola shape that looks something like that. From this point to B, the change in moment should be the area under this part of the shear diagram. I'll kind of hatch that slightly different so you can see it. That area is going to be 1/2 base. The base is 1 and the height is -5. So that's negative 2.5. And that brings us back to 0. So that works great. The slope is going to start off at 0 and end up at a negative slope. So we get a nice little parabolic section there. Now the next section, the change in moment, is the area under this part of the shear diagram. That's a trapezoid. So if you average the height, you'll get 7.5 times the base is 1, so it should be a change of negative 7.5. So I should land, again, this is where the scale is going to get off. This should be minus 7.5. And you'll notice that the slope of the moment diagram is given by the shear. The shear starts off with a slope of 5 and gets steeper. Actually ends up at a slope of negative 10. So my graph would look, again, it's going to be hard for me to draw to scale, but something like that. It doesn't have that little kink in there, but you get the idea. Now the change in moment over this last 1 meter segment would be this area, and you see these areas are equal. The area in that trapezoid is positive 7.5, so that brings us back to 0, which is great. The slope on this side goes from minus 10 to positive 10, and then decreases to not 0, but to 5. So you'd get something like that. So I know, Mr. Warburg, you said before you were talking about these kinds of switches in shear, right?
Right.
So see, sometimes the switch in shear can be such that the slope is continuous and you get a min or a max like this, or the slope can be instantaneously changing.
Okay.
So the slope here is not continuous, if you can see. But the great thing about this now is you can tell me where the maximum moment occurs and what's the value. Where is the maximum moment? It occurs over point C and is minus 7.5 kilonewton meters. The maximum positive moment is 2.5 kilonewton meters and occurs at this midpoint. So if I was making this beam out of reinforced concrete, I'd have to choose tension steel on the bottom of the beam to manage this moment, and I'd have to choose what we call compression steel, it's really not compression, but reinforcement in the top of the beam to handle this negative moment. And actually I need more of that in this region than I would of tension steel in this region. So any questions about that? Okay.